Everyone, so this video is going to be on the skeletal system overview PowerPoint that you need to know for lab. So this is what the quiz next week is going to be on. So quiz 2 will be on all the information from this PowerPoint. And most of the quiz is going to be on the definitions of the bone markings, so the projections and depressions, but I'll get into that when we get to that section of the PowerPoint. However, all this information is important and you really need to know it in order for us to get into the skeletal system. So anything from this PowerPoint is fair game for that quiz, but most of it will be on definition. Alright, so when we're talking about the skeletal system, we're really talking about three major things. We're talking about bone, cartilage, and joints. Alright, so joints, obviously, because that's where two bones meet, and not all joints are movable. Alright, some joints are immovable. Alright, so you could have two bones meet and not move. That's still considered a joint, nonetheless. But we also have cartilage involved with this, because cartilage holds a lot of bone together, and you'll see that there's cartilage between movable joints that help reduce friction and help reduce impact of those two bones meeting in that joint. So cartilage is also a very important part of the skeletal system. So I'm going to start with cartilage first because there's only three types and they're pretty easy, and we've talked about it already pretty much. Alright, so the three types are hyaline cartilage, elastic cartilage, and fibrocartilage. Hyaline cartilage is the most abundant in your body, and we looked at this in lab. Alright, that was that kind of stained glass matrix that we saw with the little lacuna and the chondrocytes in the lacuna. So we use our hyaline cartilage for a lot of things in the body. One of the things that we use it for is to hold our ribs to the sternum, so you'll find hyaline cartilage there doing exactly that. But we also find hyaline cartilage between movable joints. So all the synovial joints are going to have a hyaline cartilage layer to kind of help reduce impact between the two bones that make up that joint. We also see hyaline cartilage in a lot of parts of the respiratory system too. All right, and we looked at it in the trachea slide in lab. Well, that's important because hyaline cartilage, even though it's pretty tough and will help maintain the shape of our trachea, it also has some flexibility to it. So I can get hit in the throat and it won't just shatter and break. All right, it will bend in and then spring back, and then my trachea, my windpipe, will still be open. All right, so that's why we have hyaline cartilage in the respiratory system as well. Now, for the elastic cartilage, we only see that in a few places in the body. It's very elastic. It's very stretchy and springy. A good example of this is in your ears. So your ears are made up of elastic cartilage, and you can see how much they bend and spring back. But another place we see it is in the epiglottis. The epiglottis is that structure on top of your larynx, all right, that will close off your larynx when you swallow, so food and water doesn't go down into your respiratory system. Now, because this is so stretchy, it makes a nice tight seal against that larynx and prevent any type of fluid or food to get down into your respiratory system. And then finally, we have fibrocartilage. Fibrocartilage is really good at taking on compression energy. So you're going to see this in areas where you have a lot of compression and need to protect your body against compression. So you see this in a lot of discs in your body, like the vertebral discs in your vertebrae. All these little discs that are between the vertebrae are made up of fibrocartilage, and they kind of help reduce that compression. We also see it in the discs in your knees. So we call these discs menisci, meniscus for singular. These are also made up of fibrocartilage, helping taking on that shock and acting as shock absorbers when you're walking around or stomping. All right, so that's it for cartilage. The rest of this is going to be focused on bone. So there are 206 bones in the human body. You will know all of them by the time we're done with the skeletal system, and not only that, you'll know most of the structures of those bones. Now, that being said, 206 seems like a lot, but in reality, we are symmetrical, so we have two of a lot of these bones, so you're actually not going to learn 206, or it's not going to take you 206 bones to learn. All right, so a lot of them comes in doubles. Okay. I don't expect you to know every single bone just yet. This is what we're going to be doing in lab for the next few labs. We're going to be focusing on the different bones. So just you don't have to know every single bone just yet. However, one thing you should know is what the skeletal system is doing for you. We've talked about this a lot, so this is kind of just review. Yes, it's being used for support and protection. All right, so support, it helps give our skeletal muscles something to hold on to, and those muscles are what's keeping us upright and giving posture and being able to move. Well, without those bones to attach to this skeletal muscle would have nothing could not work properly. It's being used for protection. A good example of that is your sternum, your breastplate here. This is a bone that is protecting the organs in your thoracic cavity. So that's a good example of protection. Or your skull bones is protecting your brain. Movement, obviously pretty important because joints are going to be made by bone and bone coming together. Mineral storage, we talked about this. While there are many other minerals that are stored in bone, they're to much lesser extents. The major thing that we store in bone is calcium. That's a very important mineral for a lot of function in your body. We also are going to make blood cells in bone. So this is usually made in red marrow. So we'll talk about red marrow, but that's where we're going to make all the blood cells, both red, or all three, red, white, and thrombocytes. And then finally, we also have yellow marrow, which is going to be a fat storage, and we're going to store triglycerides there. So we don't only store triglycerides as adipose tissue, as fat in our body. We could also store it in our bone as well, and that's really where yellow marrow comes in. It's that triglyceride storage. All right, so we need to talk about how we can categorize a lot of these bones, because remember there's 206. One way we can categorize it is by their function. So they could either be in the axial skeleton or the appendicular skeleton. All right, so with the appendicular skeleton, the root word here is appendage. These are going to be your appendages. All right, so your arms and legs, the bones of your arms and legs. These bones are more designed to help you move and move throughout the world or move objects, just to move, right? That's mostly what they're being designed for. So your appendicular skeleton is not just the bones in your arms and legs, but also what they attach to, because they're also being used in movement. So that's going to include your pelvic girdle and your pectoral girdle as well. While the axial skeleton is pretty much everything on your center axis, and this is going to be more for support and structure. All right, so this is going to include all your vertebrae, your sacrum, all your ribs, all right, your skull, the bones, the vertebrae in your neck. All of this is going to be considered part of the axial skeleton. Even though they do have some movement, they're not mostly being used for movement. They're mostly being used for support, all right, and to hold you upright. All right, the next way we can classify bones is by their shapes. All right, so there's four major categories here. There's long bones, short bones, flat bones, and irregular bones. All right, long bones, pretty self-explanatory. They are much longer than they are wide. All right, we see this a lot in the appendicular skeleton. Short bones are going to be about as long as they are wide. Good examples of this are your tarsals and carpals, so your wrist bones and your ankle bones. A lot of those are going to be short bones. We can also have flat bones where the bone is really flat, so your sternum is a good example of this, and the bones of your skull are also a good example of this, are nice and flat and thin. And then if something doesn't fit nicely into those three categories, then we just throw it into the irregular category. And this is mostly reserved for your vertebrae, because your vertebrae are very oddly shaped and they don't fit nicely into one of these other shape categories. All right, so next thing I'm going to talk about is bone markings. This is what the quiz is mostly going to be on next week. So for this, you need to know these terms, their definitions verbatim. And by verbatim, I mean word for word. All right, so I'm not going to go through every single one because this is going to take you memorizing this. All right, I can talk about it, but it's not going to do you any good. You're just going to have to make flashcards of however you learn to really just get to know these terms. However, I do want to clarify some of the ones I see students get confused a lot, and some of these definitions, the words in the definition themselves you might not know, so I'll try to clarify those as well, but you might need to look up some of these terms just to really understand what you're reading and learning. All right, so as far as bone markings go, they could fit into two categories. We have projections, which is anything sticking out of a bone, and we have depressions or openings. So they could be a hole going through the bone, or it could be like an indentation down the length of the bone. All right, so they have different function in your body. All right, they're both being used for something. So projections, things that are sticking out of the bone, are usually going to be used for attachment points. All right, so sometimes you'll see muscle or ligament attached here, but you can see other things attached here too. Sometimes you have bone and bone attached together in a joint, and that's what those projections are being used for. But again, things sticking out, it's mostly going to be used for attaching. While depressions and openings are going to allow things to move through or along the length of bone. All right, we have tons of blood vessels, nerves, lymph vessels running through our bodies. They're going to have to escape bone somehow, and so they're usually going to do this through a hole or opening through that bone, and so it'll grow right through the bone. Or it could grow down the length of the bone in a depression and be snug against the bone and slightly protected by that bone. All right, so here's some of the terms that you're going to need to know. These are all the projections that you need to know. So I do want to clarify some of these. The first one I want to clarify is a tuberosity versus a tubercle. All right, these are both rounded projections. That's both in the definition for both of these, but there's a difference in size here. So tuberosities are usually larger, while tubercles are usually smaller. Not only that, tuberosities are usually roughened too. I mean, you'll see this with tubercles, but tuberosities more so are going to be roughened. And having a rough surface is actually really important for a bone, because remember, these are projections, they're sticking off. So we have this round projection that is rough. But if this nice round rough projection, ligament or other things can attach to that rough surface a lot better than it would be if it was just smooth. All right, so even though it says tubercle is small and tuberosity is large, you're going to see situations where that's not really the case. They mostly mean on the same bone when they're talking about this. So if you see a tubercle and a tuberosity on the same bone, yes, the tubercle is going to be smaller than the tuberosity. However, but there's going to be instances where you see a tubercle on one bone that is much bigger than the tubercle or tuberosity of another bone. So don't let the definition stump you too much. All right, the next two I want to clarify is a crest and a line, because these are, again, very similar. So the definition for this is narrow ridge of bone for both. And by ridge, we mean kind of a point, not a point, but like a thin edge on the bone. So kind of like a mountain ridge. If you've ever been hiking, you know what a mountain ridge is. It's where you have a chain of mountains together and they make this nice thin point all the way down. So that would be considered a ridge, and that's why they're using this in the definition. But the major difference between these two is the prominence of it. All right, a crest is way more prominent, meaning you're going to have a nice sharp edge that is very defined all the way down the bone. While a line is also going to be a nice defined edge, but it's going to be shallower or less prominent is what we would say. All right, so it won't be as defined. So good examples of this would be your iliac crest. All right, so your crest is that really thin part on top of your ilium, which is your hip bone. All right, so it's nice and thin, but it's very prominent. Versus here would be considered a line. You could see it's much shallower and not as prominent as that crest. However, it's still very ridge-like. All right, the next thing I want to clarify is an epicondyle versus a condyle. So these are very similar. You probably already know what these are. A lot of times when people draw cartoon bones, they draw these structures. All right, so let me just point some out to you, and it might help explain it. So here is a condyle, and here is an epicondyle. A lot of times when people draw cartoon bones, they have these little loops on the bone, right? Well, condyles are usually smooth on the surface, all right? Well, epicondyles, and if you remember what epi means, it means on top of, so they're going to be on top of the condyles. They're going to be off to the sides, and they're going to be nice and rough. So the condyles themselves are where bone will meet bone for a joint. All right, so you could have a condyle meet another condyle, and they're nice and smooth, so there's no friction between those two bones in that joint. Well, off to the side with the epicondyle, it's nice and rough, and that's usually going to be used for ligament attachment to hold that joint together. So if you imagine another bone underneath this, also with condyles and epicondyles, the ligament would attach to the two epicondyles, which are nice and rough, while the two condyles would actually make the joint together nice and smooth. All right, next one I want to clarify is the ramus. A lot of students get stumped with this one. The definition is an arm-like bar of bone. This gets a lot of people. What they mean by that is, by bar, they mean something that joins two things together. All right, that's what they mean by a bar. So here's a ramus right here. It's this region of your mandible, which is your jawbone. So here's the ramus. This bar will bind these two processes here, one's a condyle, the other one's a process, to the main part of the mandible. So this bar is joining these things together. All right, so that's why that's considered a ramus. All right, the last thing I want to clarify too before I move on to the depressions is a facet, mostly because this chart has it wrong. All right, it has facet as a projection. It is not a projection. It is a depression. I know why they did this though. It's because of the example that they used. Okay, so here is the rib, right? Your rib has something on it called a head, which is a expansion over a narrow neck. But on the head of the rib, we actually have two facets, and I think that's why they did this. The head is actually the projection, facet is not. So a facet is a flat, smooth surface on the bone, and this is usually going to be used for articulation or making a joint. That's what we mean by articulation. So having this nice flat surface, let's say a condyle comes and meets with it, now you're going to have a joint that can make a two-dimensional plane movement. All right, we call this planar movement. All right, that condyle can slide in that flat facet nice and easy, nice and smooth. All right, so keep that in mind. Facet's actually a depression, not a projection. All right, and then here's your depressions, not nearly as many as the projections. But again, I do want to clarify some of these. First is going to be a groove. All right, so I mostly want to clarify this because look at their definition. A lot of people don't know what a furrow is, and that's what they're using, and you'll see that in medical textbooks, so it's good for you to know that term. But by a furrow, you probably don't know what that is unless you grew up on a farm. A furrow is that kind of trench that they dig out for planting crop. All right, that would be considered a furrow. All right, so that's what they mean. That's what a groove is going to look like. It's going to look like somebody dug a trench down the length of the bone. All right, so a lot of times that's going to be used for things to grow down the length of the bone, like blood vessels, but still be kind of nice and sealed against the bone and protected. All right, next I want to clarify is a foramen versus meatus because they're very similar. So a foramen is a round or oval opening through a bone, like somebody drilled a hole right through it to allow blood vessels and nerves to run through. A meatus is the same thing, but they say a meatus is more canal-like. Really, what the difference is between these two passages is the depth. All right, you could think of a foramen more like a doorway, while a meatus will be more like a hallway. All right, so much longer. All right, so you'll see examples of both. Also, I want to clarify a fissure. All right, so a fissure is a narrow slit-like opening, and by slit, they mean like a tear to open it up. So it's not going to be a nice, perfect hole or round or oval opening like a foramen would be. So it's going to be more like somebody carved it with a knife real quick or made a slit with a knife. All right, so more elongated. And then finally, I want to clarify what a fossa is too. All right, so fossas and facets, like I showed you in the previous slide, are very similar in function. All right, they're going to be smooth, and they're usually going to be used for articulation. All right, so a fossa, the definition is a shallow basin-like depression in the bone. By basin, they mean drained lake. That's what a basin is. When you drain the water out of a lake, that cavity that's left behind of the lake is a basin. So it's kind of like a bowl or a cup that is going to be in this bone that a condyle can fit into and make this joint, this kind of rocking joint in it. All right, so that's why the ones I wanted to really clarify, because I see a lot of students get stumped on those, and I don't want anybody to really be lost with these definitions. If you're still struggling with some of these definitions, you might need to look up the word of the definition as well, just to really understand where they're coming from. But they try to use terminology that will never go away. We're always going to have furrows, right? We're always going to need to farm, all right? So that's why they use stuff like this for the longevity of that definition. All right, so the last thing I want to do before I move forward is give you an example of why it's good to know this information and why I'm hounding you so hard to learn it and doing so much of it with quizzes. All right, so a lot of the structures you're going to see at the skeletal system is just going to be a combination of these terms plus the terms that we learned on the first day of class, all that language of anatomy stuff. All right, so let me give you a couple examples that might help solidify this. All right, there is something in your body called inferior orbital fissures. All right. First off, think of what orbital means. All right, we're referring to the orbital cavities there, and those orbital cavities are the cavities that house your eyes. It's your eye sockets, right? So if you look inside the orbital cavities, you will see fissures. All right, slit-like openings. Here's a fissure. Here's a fissure. Well, since we have two, we've named one from another. This one's below this one, so this is the inferior orbital fissure, while this one is called your superior orbital fissure. So by knowing the term from the first class and knowing these terms too, you could put the puzzle pieces together to really understand these structures instead of just trying to hard code each one of them into your brain. All right. So hopefully that gives my point across of why it's so important to know a lot of these structures and the terms that I've been going over. All right, the next thing I'm going to talk about, all right, so before I move on, like I said, most of the quiz is going to be on that information, but there still could be questions on the rest of this stuff too. Next thing we talk about is bone texture. There's two major textures to bone. There's compact bone. That's the bone that we looked at in lab already, if we've had lab. If not, it's the one that you see in the video when I talk about bone. And there's spongy bone. All right, both are made up the same material, but their texture is a little different. Here is compact bone. Compact bone is where all those osteons fuse together. You don't have osteons in the spongy bone, though. Instead, you have these little pillars called trabeculae, and it creates this open chamber through the spongy bone. Now, this open chamber is not just open chamber. This is where you're going to find a lot of red or yellow marrow is in the spongy part of the bone, and you're going to find tons of blood vessels and nerves running through all of this. All right, so your bones are very innervated and they're very vascularized. You're going to have tons of blood vessels and nerves running through this. Compact bone is usually going to be found on the outside of bone, just to protect the bone, while spongy is going to be towards the center to house everything. All right, next thing we need to talk about is the parts of a long bone. All right, you're going to see these terms quite often. All right, so there's three major regions to long bones. All right, so first is the diaphysis. The diaphysis is the main shaft. Here is your diaphysis right here. All right. Inside your diaphysis, you have an open cavity right in the center of it called your medullary cavity, or the medulla of the bone. All right. This open cavity is where you're going to find a lot of different types of marrow. All right, so as adults, actually, you find yellow marrow here, that triglyceride storage, but when you're a child and still developing, this is actually all red marrow, helping to add to your blood development. All right, and then outside the diaphysis, we have epiphyses, that's plural, epiphysis for singular. So we have an epiphysis here and an epiphysis down here. And we distinguish one epiphysis from the other by how close they are to the point of attachment of the body. So here would be the proximal epiphysis, here would be the distal epiphysis. Now in your epiphyses, you have another structure through the spongy bone called your epiphyseal line, and you can see that right here. This is where we used to grow when we're having our growth spurts and our bones are elongating. So before we reach adulthood, all right, when we're juveniles still growing, this is all hyaline cartilage, and we call this the epiphyseal plate or growth plate, all right, during that time. Your bone actually starts off as hyaline cartilage. Hyaline cartilage will grow first and lengthen the bone, and then right afterwards that hyaline cartilage will ossify and become bone. Now once we hit adulthood, we stop growing, all right, and this will ossify over entirely, and that whole process will shut down because now we just have solid bone at our growth plates, now known as the epiphyseal line instead of plate. All right, next we need to talk about the composition of bones. So there's really only two things that contribute to the bone's matrix. There is the organic substances and there's the inorganic. The organic substances is going to be your collagen fibers, your elastic fibers, that ground substance, all the stuff that has carbon in it. All right, so that's all going to be considered the organic parts of the matrix. Well, the inorganic is going to be the minerals, mostly calcium. All right, that is not organic, that is inorganic. Now, these give two different properties to bones, though, that's really important. So your organic gives bones flexibility. All right, your bones do have flexibility. Even though they seem really hard and rigid, they can bend without snapping. All right, and you need that. Like if you jump from a high surface and you land on the ground, your bones will bend a little bit, but then spring back, and everything will be fine. But at the same time, they are rigid as well. That's coming from the inorganic. The inorganic was providing that stiff rigidity of bones that I'm sure you're aware of. Okay, so you need both for bones to function properly. Now, you could do a little experiment at home if you want to see these two properties in action. This is a cool experiment. We can't do it in lab because we don't have an oven, but it might be beneficial to you if you want to do it at home. All right, so if you remember, organic gives bone flexibility, inorganic gives it rigidity, right? Well, you could take chicken bones, because chicken bones are very similar to our bones. You could place one chicken bone in vinegar and leave it overnight, and then take another bone and bake it in the oven for an hour at like 400 degrees Fahrenheit, all right? Well, what happens with both of these two different processes, the bone that is in the oven, when you bake it, you're actually killing off or burning away all the organic compounds of the matrix. So when you take that bone out of the oven, all that's left is the inorganic stuff. And if you remember, the inorganic gives the bone rigidity, and the organic that we lost was what gave it flexibility. So if you took that bone and tried to bend it now that it came out of the oven, it will snap. It will have no flexibility to it, and that's because it's just the inorganic left. Now that other bone, though, that you put in vinegar overnight, that is going to dissolve all the inorganic. All the minerals are going to dissolve out into the vinegar, and you're just going to be left behind with the organic parts of bone. All right, if you remember, the organic parts give you flexibility. So when you take that bone out of the vinegar overnight and you try to bend that bone, you will be able to bend it entirely. You could bend it all the way where the ends touch each other without the bone snapping. And that's because we got rid of all the we got rid of all the inorganic rigid stuff, and we're left behind with the organic flexible stuff. All right, so also be aware of a lot of the terms that we talked about with the tissue lab. All right, so you need to know osteons, canaliculi, lamellae, lacuna, central canals, osteocytes. So I'm not going to go over that again because there's a video of that you can go check out if you're still confused about a lot of those structures. The only new structure I'm really going to introduce here is called the perforating canal, also known as the Volkmann's canal, but we're trying to get away from naming things after scientists. Perforating canal is this kind of canal right here that runs perpendicular to the central canals of the osteons. So here's my central canal with blood vessels and nerves running through it. Here is the perforating canal. So this takes kind of like a 90-degree angle and will bridge the gap between the central canals of the compact bone to that open space of the spongy bone. So now blood vessels can grow through the spongy bone, but also get into the central canals and grow through the compact bone as well. So everything's kind of connected, nothing's isolated here. All right. I also need to talk about how we grow as an adolescent, so especially with your long bones. So if you remember me saying that that epiphyseal line after it ossifies was called the epiphyseal plate. So here's an epiphyseal plate here. This is hyaline cartilage. So we have hyaline cartilage here when we're growing, and we'll add new hyaline cartilage on each end in the epiphyses and lengthen the bone that way. So we just keep on adding to it and lengthening the bone, and shortly after that, that will ossify into bone tissue, and that's really how these bones are growing when you're going through your growth spurts. But once we become an adult, this will ossify over, and once that hyaline cartilage is gone, we stop growing. All right, and we actually stop growing because that hyaline cartilage is gone. All right, so that was the main part. There's still a couple more terms you should know for the quiz, just mostly because you see these terms over and over again. Okay, so the first one is a visceral skeleton. So your visceral skeleton is the bones or the parts of your skeletal system that are developed from your gills. All right, so you have gills, or you had gills when you were a fetus. Gills are one of the first structures that we develop as a fetus, and it's very similar to the gills of a shark or a fish or something. You're gonna have gills as a fetus, but they don't stay that way, or at least we don't stay that way. So that's one of the first structures we develop, but after time, those will differentiate into other structures. All right, they grow to be gills, and then they turn out to be something else. Well, some of the bones in your body come from those gills. So those bones that came from your gills we call the visceral skeleton. So a good example of that is your hyoid bone. Your hyoid bone is part of your visceral skeleton. It is a bone that floats right here in your neck. That's not actually attached to the rest of your skeletal system. And this is where a lot of the muscles of your tongue attach to, is this bone that floats in your neck right here. All right, so that's what we mean by visceral skeleton. Next thing you need to know is a concave. So concave are scroll-like bones, so bones that kind of fold and are like rounded, kind of. It's kind of hard to explain. They're folding, all right? So you can see them here and here, all right, these kind of folding structures. These are there to increase surface area. So you find these in your nasal cavity. We call them nasal concave, concave for singular. And by having these scrolls on the lateral parts of our nasal cavity, we're increasing the surface area of our nose, which is really important, mostly because breathing through our nose is actually more beneficial to your lungs. All right, so when you breathe through your nose, and because we have all this extra surface area, you have tissue that grows over these concave. All right, so you also have capillaries that are growing over these concave. So now we have this air interacting with all these capillaries and all this tissue before it goes any further in your respiratory system. And what that's doing is humidifying that air, because there's tons of mucus and wet stuff in your nose. It's humidifying that air. It's also warming that air. These capillaries are bringing heat from the rest of your body to the capillary, and that will warm that air coming in. Now you want that, so because when you breathe in, and you breathe in this humid, warm air, when it goes down into your lungs are made up of simple squamous cells that are very sensitive. All right, so by having this humid, warm air, it's going to protect those simple squamous cells a little bit better. Now, if we didn't do this, and that cold air gets in, you're going to dry out your simple squamous, and it can crack if it's not, or same thing, if it's dry or dry, it will also crack the simple squamous cells. So you kind of need this wet, warm air getting in there. All right, so that's also one of the reasons why if you've ever run when it's cold out, it hurts to breathe through your mouth. That's because you're actually damaging your simple squamous cells by doing that. And if you start breathing through your nose, it gets a little better, and that's because we have all this extra surface area and they're warming and humidifying that air. All right, so we do have 3 concave on each nasal cavity. Again, they're on the lateral surfaces, and you can probably figure out the names of these. So we have a superior nasal concha, a middle nasal concha, and an inferior nasal concha, left and right. All right, the next structure you need to know are sinuses. A sinus is just a cavity in the center of a bone. This is really interesting. There's a lot of theorized reasons why we have this. Nothing too definitive, but also it's kind of hard to prove why we have this entirely. But let me give you reasons why we believe we have these structures. So you mostly find your sinuses in the bones of your face. And you'll see a lot of these bones have these open chambers that are inside the middle of the bone. Now, these open chambers are not completely closed off. There are small channels that get into these sinuses, so they do have access to, let's say, your nasal cavity or something. So they will all be connected somehow, but they're usually, for the most part, closed off, and they're mucus bound. All right, so three things that we really think we have these for. One is for resonance. All right, humans have very defined sinuses. All right, and when we talk a lot, right? So we could resonate our voice more by having these open chambers, and it makes your voice more booming by having these open chambers. And that's why when you get a sinus infection, you sound more nasally. All right, because you're not having that big booming sound coming through these sinuses. Another reason why we think we have this is as a compression zone during impact. All right, so if you think about this, if not being open, let's say a solid bone was here and something hit this person in the face, that solid bone runs the risk of being lodged into the brain and that person would die, right? But now we have these compact zones or compression zones. So if something hits this person in the face, this will all crinkle together like a soda can and dissipate that energy so nothing gets lodged up into the brain. We actually use this same concept in cars. If you ever looked under the hood of your car, you'll notice that the engine of your car is not directly touching the front or the chassis of the car. It's kind of just floating there with open space around it, and that's giving you that kind of compact zone. So if you get into an accident at the front of the car, everything will crinkle together and dissipate the energy, and nothing will be lodged into the cab. All right, so your face is doing the same thing. Now, the last theorized reason why we have this is to give a nice open, wet, dark area for bacteria to grow. All right, we breathe in a lot of bacteria when we're breathing, right? Well, we don't want that bacteria inside our respiratory system that is sensitive. Instead, we have these open chambers where the bacteria might take a corner and then go here instead and start growing there instead of growing somewhere where you could really run the risk of getting seriously hurt, right? So that's one of the reasons why we think we have this as kind of like a labyrinth or a maze for these bacteria. And once they start growing in your sinuses, because we do get sinus infections a lot, so that does happen. Once they start growing in your sinuses, though, your white blood cells can go and take care of them then. And that way, your sinuses are being infected instead of more of your sensitive organs of your respiratory system being infected. All right, and the last thing we talk about is fontanelles. You've probably heard of fontanelles before. It's the soft spots in fetal skulls. We have fontanelles up until we're about 3 years old. By 3 years old, they ossify to be solid bone. So before that, though, the bones of your skull are not fused together. Your bone or your skull is not one giant bone. It's multiple bones that fuse together later on in life. All right, and you can see the individual bones in this image here. All right, we have tons of different bones that are all separated. Well, they're separated by this really soft tissue that is that you find around a lot of these bones, and we call these fontanelles, the soft tissue. Now, there's two reasons why we have this, two really important reasons. And like I said, we don't ossify this until we're about 3 years old. All right, so you can probably guess what these reasons are going to be. All right, so the first reason is during labor, we can get out of the birthing canal without damaging the mother or damaging ourselves when we're being released. All right, so our brains or our skulls can compress and get out of that the vagina and the birthing canal pretty easily. All right, and then if you ever noticed, or you may have noticed, but I'm sure you've heard that most babies are born with a cone head. Well, that's why, because they have these fontanelles and all this stuff can kind of smush together and just kind of come out pretty easily. That cone doesn't stay, though. That cone will dissipate and your skull kind of goes back to its normal shape afterwards. All right, so that's one reason. The other reason, and the reason why we don't ossify this until we're about 3 years old, is because from birth to about 3, our brains developed very rapidly, actually outpacing the rest of our body. All right, so by having these soft parts in our skull, it allows our brains to grow pretty rapidly and not be confined to the skull that would be solidified. All right, so our brains can grow rapidly at that time. And then at 3 years old, we ossify and our brains kind of slow down in development, and our brains kind of just grow with the rest of our body at that point instead of outpacing it. So that was why we don't need it after 3 years old. Okay, so that's all the terms that could be on the quiz. Like I said, it's mostly going to be those definitions and knowing those definitions verbatim. But again, I could pull questions out of anywhere in this PowerPoint because all this information is really important for you to know in order to get into the skeletal system. All right, so again, we're going to take quiz 2 Monday and Tuesday, depending on which section you're in. It's going to be the first part of class, first 15 minutes, and then we're going to get into the skull bones. That's So if you are Monday, Wednesday classes, you could sign off now. I have nothing to say to you. Everything's pretty much set up because we haven't missed that much. We only missed one class. However, if you're Tuesday, Thursdays, I do need to talk to you a little bit. And I've already written this in an email, but I'm going to say it to you now verbally through the video. So they still have not given word yet if we're going to have Thursday off or not with the storm. If we meet Thursday, that would be the best scenario. We'll come in Thursday. We will take quiz 1 based on all of the language of anatomy chapter, right? And then we're going to spend the rest of the time looking at slides of everything that we've missed the last 2 classes, okay? So everything that we were supposed to cover last Thursday when I was sick and everything that we're supposed to cover today because of the storm, we will go through all those slides on Thursday. So it's up to you to watch those videos and get the information beforehand before coming in, because I'm going to just let you do your thing, all right? That would be great, because then we could just jump on into the skeletal system on Tuesday, okay? All right, if that does not happen, then we're kind of in a little bit more trouble. So if Thursday is shut down, all right, we're going to take quiz 1 online, and I'll make sure it's due at 11:59 on Sunday of this weekend. All right, there will be a time constraint to this just to make sure that everybody studied this stuff and is not just flipping through the book. Once we're done with that, then we are going to try to find another time for you to come and see all the slides you missed with tissue. All right, so it's still up to you to watch those videos and get all the background information, but now we're probably only going to have time outside of class to really see it. So to try to give everybody the most time possible, I'm going to spend my office hours next week in lab so you can come and take a look with the microscopes and the slides at your leisure. All right. I will also be there on Tuesday and Thursday from 12 to 1 during my gap between the classes for anybody who could not make it during my office hours of that week. All right, so there's going to be opportunity for you to come in, but it's going to have to do outside of class time, because class time next week is going to be focused on skeletal system, because now we're falling behind and you need to know this information before I can sign off that you've passed this class. All right, so hopefully that doesn't happen, but if it does, that is the worst case scenario. Quiz online, finding time to look at these slides somewhere else outside of class. All right, so even though that might be difficult, the most important thing is everybody's safety. So I hope everybody's taking the right precautions with the storm and everybody's feeling comfortable. And same thing with your family. I hope everybody's going to be fine. I'll let you know if anything changes in the future and if I get any information from the university on what to expect and what we should do. Okay? But take care of yourselves, and I will see everybody next week unless I see you Thursday.